This is it. This is the Sudoku you have all been waiting for. This is the Sudoku that I have hyped up in both of my last two Sudoku videos, and I am sure you have all been frantically refreshing YouTube for the last 7 days to see when I would upload this video. Okay, maybe not, but still, I'm very proud of this puzzle. This is a puzzle that I have spent a very long time perfecting and getting just onto that borderline between being reasonably possible for a human to solve and just not. And I think I've got it just within that borderline. I think it is possible. It's fiendish though. It is very difficult. So, without further ado, what are the rules? Well, firstly, normal Sudoku rules apply. So each row, column and 3x3 box must include the digits 1 to 9 exactly once. Disjoint groups rules apply, i.e. digits must appear in each position within a box exactly once. So for example, this 1 is in the top right position within its 3x3 box, so it can never appear in any more top right positions within a box. And effectively what you get is kind of like a 3x3 box in all of the top right positions, because those highlighted squares are the digits 1 to 9 exactly once. So it's like an extra 3x3 box that's kind of popping out into the fourth dimension, ahead of, in front of the Sudoku. I don't know. That's the way I see it anyway. It's like a 4-dimensional thing. Hence the name Tetra in the title of this puzzle. It's a little bit tenuous. Maybe I need a bit of practice naming my puzzles. But yeah, Tetra Terror, because the 4-dimensional link, and it's difficult. It's hopefully terrifying. So that is the disjoint groups rule, and obviously that's not just applicable to the top right corners of each box. It's every position within each 3x3 box. Anti-knight rules apply, and that means that cells and knights move apart. For example, these two along and 1 in a 90-degree turn from the 2 along. And knights move apart in chess cannot be the same. So those can't be the same digit, those can't be the same digit, etc. Negative diagonal rules apply. That's basically just a clumsy way of saying that this main diagonal marked is one set of the digits 1 to 9 exactly once each, and there cannot be any repeats on that. Arrow rules apply. So on an arrow, the digits add up to the number in the attached circle, and those two add up to that. And just for clarity, these arrows are separate arrows. In other words, this adds up to that digit, and these two cells separately also add up to those that digit, and the same applies over here. And the Kropke dot rules apply, i.e. cells joined by a white dot are consecutive. These are consecutive pairs, and those are the rules. So if you want to face up to the Tetra Terror yourself, it is fiendish, but I do think it's humanly reasonable, humanly solvable. Yeah, do have a go. There is a link in the description to somewhere you can see this exact page and have a go yourself. Otherwise, if you just want the humanly possible solution demonstrated, then, well, here we go. And the first thing to notice, well, you might notice, first of all, that these are 6, 7, 8, or 9, because a 3-cell arrow, well, the minimum it can be is 1 plus 2 plus 3, which equals 6, so it must be at least 6. But unfortunately, that information right now is not very helpful. So what we need to do instead is some set theory, which is really cool, and I've seen set theory applied in all sorts of different ways in Sudoku, and it's always done very cleverly, and it's always very satisfying when you see it and when it works. I've never seen it done in this particular way. That's not to say that it hasn't been done in this particular way, of course. There are Sudokus being made all the time. But anyway, the set theory that we need to do here is as follows. Let's highlight every top left cell within the 3x3 boxes. Let's make them all red. Okay, well, because of the disjoint groups rule, we know that this is a set of the digits 1 to 9, exactly once each. Okay, now let's do exactly the same with the middle cells of each 3 by 3 box. That's another set of the digits 1 to 9, exactly once each. And the bottom right cells of each box is another set of the digits 1 to 9, exactly once each. So we have now highlighted 3 sets of the digits 1 to 9, exactly once each. Okay, well, as it so happens, we've also managed to highlight the entire negative diagonal. And we know that digits cannot repeat along the negative diagonal. In other words, this is a set of the digits 1 to 9, exactly once each. So if we take one set of the digits 1 to 9 away from 3 sets of the digits 1 to 9, whoops, there we go, we are left with 2 sets of the digits 1 to 9, exactly once each. And that's exactly what we have in our highlighted red region, 2 sets of the digits 1 to 9. Well, what do we know about 2 sets of the digits 1 to 9, exactly once each? Well, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 is 45, so 2 lots of that is 90. So the red region as it is at the moment in its current highlighted state adds up to 90. Okay, well, we actually have a lot of information about these red highlighted regions because of all of the arrows that we have along them. It's no coincidence, you know. So we can describe this kind of semi-diagonal as 3 times that, because we've got, let's say that's a 7. No, let's try again. The 7. Then these 2 add up to 7, and also these 3 add up to 7. So we've got 1 lot of 7 there, 1 lot of 7 there, and the 7 itself. So it's 3 times 7, or 3 times whatever is in that middle circle. And we can say exactly the same about this. That bit is 3 times whatever's in there. And we can say a similar thing about that. That highlighted region is 2 times whatever is in there. If that's an 8, then it's an 8 there plus 2 digits that add up to 8. So it's 2 times 8 in total. Okay, well, we know that the red region as a whole adds up to 90. So we can say that 3 times that plus 3 times that plus 2 times that plus these 3 cells here must add up to 90. That puts an awful lot of pressure onto these 3 cells to be very big. So let's just go straight into a very blunt question. We know these have to be different, but this one could be anything. So let's just go straight into the bluntest possible question and ask, can this be anything less than 9? Let's assume it's 9, and let's ask, can it not be that? That's our hypothesis. Okay, well, let's try 8, the next possibility down. And let's maximize these 2 by making them 9 and 8. I've done them in that order because this cell gets to be multiplied by 3, so the bigger the better in terms of maximizing it, and then that is obviously the next highest number. Okay, well, 8 times 3 is 24, plus 9 times 3, that's 27, so that totals 51. Plus 8 times 2, that's 16, so 51 plus 16 is 67. Take that away from 90, and we're left with 23. So those 3 digits have to add up to 23. And that seems okay, but the thing is there's only one way to make 23 out of 3 separate digits of a Sudoku, 3 different digits, and that is 6, 8, and 9. And that gives us a bit of a problem, because this 8 sees that cell by normal Sudoku and sees these 2 cells by Knight's move. So this cannot be 6, 8 and 9 if there's an 8 there. So that doesn't work. And if we made this any less, any lower, if we made that 7 for example, we get 24 plus 27 plus 14. That's 65. These would have to add up to 25, and that's just not going to happen. So whatever we do, however we make this work, an 8 cannot go there. Can we make a 7 there? Well, if we maximise these That's just going to mean these have to add up to 26, I think it works out as, and that's just not possible within one box of a Sudoku. So that just cannot be anything less than 9. Okay, now let's ask, once we've got rid of all of this, can these two cells be anything less than 8 and 9? Okay, well let's try putting a 7 in one of them. Let's try putting it here, because a 7 there does the least damage in terms of kind of taking the total down. And let's maximise this one. That's a 9, hypothetically. Okay, is that possible? Does that work? Well, we've got 9 times 3, that's 27, plus another 9 times 3, that makes 54 in total. 7 times 2, that's another 14, so that's 68 in total. So we need these 3 to add up to 90 minus 68, that's 22. Now, there are 2 ways of making 22 with 3 different digits in a Sudoku. You can either do 5, 8 and 9, or 6, 7 and 9. But what do they have in common? The 9. And with a 9 here, we can't make that work in any way. So that doesn't work. We cannot have a 7 there. And if we change it at all, if we make it any less, then that's just going to mean that these either still need a 9 in them to reach the required total, or they're just plain impossible. So whatever we do, if there's a 7 or anything less in either of those 2 squares, it breaks. So it needs to be an 8-9 pair. Okay, so let's assess these 2 options then. Let's try having the 9 here and the 8 here. So again, 27, because 3 times 9, plus another 27, plus 2 times 8, that's 16, so 54 plus 16, that's 70. These 3 would then have to add up to 20. And there is only one possible way of doing that without using a 9, because, as we said, the 9 sees all 3 squares. And that only one possible combination is 5, 7 and 8. Okay, now let's try the other way around. If we put an 8 there and a 9 there, then 3 times 9, 27, plus 3 times 8, 24, so 51, plus 2 times 9, 51 plus 18 is 69, so that leaves 21 left over, and there is only one way of making 21 with 3 different digits that aren't 9, and that's 6, 7 and 8. So either way, we definitely have a 7 and an 8 in those 3 cells, and then it's either it's a 6 if that's an 8, and a 5 if that's a 9. Well, we don't know it's there. It could be any of these 3. But anyway, that's what we've got. An 8 and 9 there. Good. We can also say that there is definitely an 8 in one of those 2 cells, and they are both top left cells. So we definitely have our top left 8, which means that can't be an 8. But that's about as much as we can narrow down for now. Right, the next step is to look at the 1s. Now remember, in the red region, we need 2 copies of every digit from 1 to 9. We said that this is 2 sets of the digits 1 to 9. So we need to find 2 places for 1s to go in this this arrangement. Okay, well, this 1 tells us that it can't be here. We know, obviously, it can't be in the circles there. It can't be there by normal Sudoku, and it can't be there by Knight's move. Can it be in either of those 2? Well, if it is, then it will get paired with an 8, but we definitely have 2 8s in our red region already, so we can't have a 1 in either of those 2. So we need 2 1s in these 6 cells. Obviously, 1 must be in the top box, 1 must be in the bottom box, and that's the 1s sorted. Right, it's at this point where it becomes very difficult to know what the correct question to ask is. I did release a video a few weeks ago called Anti-Parity Neighbours Sudoku, which was, I thought, a really good Sudoku. I was really proud of it, except for one step near the beginning of the solve, where basically you narrow it down to 2 options, and you just have to go through one of those options. You have to guess one of them and go through it until eventually, a little way down the line, you reach a contradiction. And that's not a particularly satisfying way of solving a Sudoku. It's bifurcation. It's not particularly logical. It's not fun. So so that is an annoying step that undermines the rest of the solve, I think. With this one, I don't think the level of bifurcation required is nearly as much, but it is difficult to know what the correct question to ask is. And in this case, the correct question to ask, not that you would immediately think of it looking at a grid like this, is if this is a 9, where do the 4s go? Okay, so let's just play this out a little bit. Obviously that would become an 8. Where do the 4s go? Well, we can't put a 4 in here because that would mean that in order to complete the arrow, that would also have to be a 4. And for a similar reason, we couldn't put a 4 along this arrow because once you combine it with the 1, that makes 5, so the last cell would have to be another 4, and we'd end up with 2 4s in the box. And for exactly the same reason, we couldn't have a 4 in here. So we'd end up with 4s in both of those arrows, and they would obviously both have to be paired with 5s in order to add up to 9. Now this becomes a problem because then we end up with 2 5s in our red region, and that completes the 5s because we only have 2 copies of each digit within the red region. But if you remember, having a 9 here is the version of events that results in a 5 going in this area. So that clashes. We can't have 3 5s in the red region, and unfortunately by putting a 9 here and asking where do the 4s go, we end up with 3 5s in the red region. So because of what we proved earlier about the red region being 2 sets of the digits 1 to 9, that breaks. And from there you can prove that that is an 8 and that is a 9. It's a difficult step and it is a little bit bifurcatory, I will admit, but I think if you're staring at it long enough and thinking about it hard enough, I think it is possible to reach that conclusion. Okay, right, the next step, the next question to ask is a little bit more obvious. It's where do the 7s go in the red region? Well, we've got one here. Oh no, actually before we do that we can do something very quickly. We know that putting an 8 here makes this a 6, 7 and 8 because 9 times 3 plus 8 times 3 plus 9 times 2 is 27 plus 24 plus 18. That's 69, so these 3 have to add up to 21. And the only way to do that without using a 9 is 6, 7 and 8. So let's just get rid of those corner pencil marks. And those are definite digits within those 3 cells. Good, okay, now back to the question. Where do the 7s go in the red region? We've got one of them already, so we just need one more somewhere in the red region. Can it go here? Well, no, because it would end up being paired with a 1, and there's a 1 there in the box already. Can a 7 go on a 3-cell arrow? No, because then it would be a 1 and a 1, or a half and a... yeah, it's not going to work. 7's too big for a 3-cell arrow like that. So there must be a 7 on one of these. So we know that one of them is a 2-7 pair. That's not particularly elegant notation, but we're about to fix it. It's about to become clear, because the next question is, once again, where do the 4s go? Now we've already proven that we can't put a 4 in here because then it would end up being a 1 and a 4 and another 4. And we can't put a 4 in here. And we need to place 2 4s in the red region. We can't put both of them in those 2 arrows, so one of them will have to go along here and the other one will have to be on one of those 2 arrows, along with a 5 to complete the 9 arrow, to add up to 9. So we know that one of these is a 2 7 and the other one is a 4 5. Okay. Now we've got a 1 and a 4 along this arrow, so what's left to add up to 8? 3. So 1, 3, 4 goes along there. And now we've just got 5 cells left in our red region that are, as of yet, unaccounted for. Well, we've got the 1 in one of those. What else are we missing? Well, we know that we've only got 1, 2 there's only 1 2 in these cells, so we need another 2 somewhere along here. Let's just put a 1 in the middle there. We've only got 1 3 in the red region so far, so we need another 3. We've got both of our 4s. There's 1 there, one in one of those 4, and then another 1 here. We've only got 1 5 because there's a 5 somewhere in here, but only one of them, so we need another 5 in here. And we've only got 1 6, and that's over here, so we need another 6 in here. And that is our 5 remaining digits in the red region. So these 5 highlighted cells are all 5 of the digits 1, 2, 3, 5, and 6. And there we go. That is our red region finished for now. We'll come back to it soon, no doubt. All right. Let's talk a little bit more about 9s. So, where does a 9 go in this box? Well, by normal Sudoku it's not there, by Knight's Move it's not there, and also we can never have a 9 on a 2-cell arrow. So it's one of those 3 positions. Let's have a look at this box. Much more straightforward. It's not there by normal Sudoku, and it's not on a cell where we already have marked digits that aren't 9, so it's one of those positions. What about this box? I know these seem like very excessive pencil marks for now. You wouldn't usually mark in 4 possibilities, but these are relevant, and I suppose knowing that they're relevant is not something that's immediately obvious, but let's carry on. So 9s can't go in there. 9s also can't go in there by Knight's Move, so there are 9s in those positions. Now, having done all of those markings, there is something more we can tell about 9s. Can we put 9s in here? Well, if we do put 9s in here, then a 9 ends up going in here because it can't go in here anymore. Whoops. And then where does it go in the top box? Well, it can't be there by normal Sudoku because there's a 9 in one of those 2. It can't be there by normal Sudoku because we're saying there's a 9 there. And that 9 there also rules out that by Knight's Move. So if we put a 9 in either of those, we end up breaking the puzzle. So there is definitely a 9 there or there. Now that we know that, we can do a little bit more. Well, actually, before we carry on down there, let's just look at this box. It's not there or anywhere where we already have things marked in. So rather trivially, those 2 are our possible 9s there. And we can also say that that's not a 9, because if that was a 9, it would be consecutive with that. And the only way to have a 9 on a consecutive pair is to make this an 8. But that clashes by Knight's Move. So that is not a 9. Okay, now let's look into this box. Where does a 9 go in here? Can't go there by normal, and the 9 either there or there means it also can't go there. It's also not in a marked box, so it must be there or there. Now, this bit I think is quite fun. And I think it's simple enough to see once you're staring at the grid for long enough. Let's hypothetically put a 9 here. Well, if we put a 9 there, then in this box it has to go here. And then in this box we're stuck. Because, well, we know it's there or there, but if it's there and there, then by the disjoint groups rule, then both of those end up getting ruled out. So it cannot be there and there, so it must be there and there instead. Those are our 9s. We can do a bit more with 9s. In this box now it's ruled out of here and here by normal Sudoku, and the 9s here or here means it can't go there, and by Knight's Move it can't go there. So that is a 9, and that resolves that for us. And that 9 sees those 2, the latter by Knight's Move. So we've got 9s there or there, there or there, and there or there. Alright, so that's quite a lot of progress with 9s. Now let's see if we can make any similar amount of progress with 8s. Okay, again let's do some rather generous pencil markings. Starting in this box, It's ruled out of these two by knight's move, so it's one of these. Obviously it can't go in a cell that's already marked. And in the middle box, where can it go? Well, it can't go there by normal Sudoku. Can't go in there by knight's move, so it's one of those. Can it go there? Well, if it's there, then this ends up being a 7 or a 9 because of the consecutive rule. Obviously, it's a 7, but then the 7 on the arrow implies that this circle must be bigger than 7 in order that 7 plus something adds up to it. But it can't be 8 and it can't be 9, so that breaks. So we can't have an 8 there. So we have our 8s in one of those 3 positions. And then in the bottom box, well, it could go pretty much anywhere in the bottom box. But let's do another hypothetical. Let's say there's an 8 in one of these two. If there's an 8 in one of those two, then in the middle box, that would be the only legitimate cell left. Then we would have a lot more information about this box. It couldn't go here by normal, here by normal, here by knights, and here because it's obviously already marked. So that would end up being an 8. Now in this box, well, we already actually know that there is an 8 either there or there because of our 6, 7, 8 logic, and an 8 in the bottom middle box there would put the 8 here. So let's just highlight those. Oh, red was a terrible decision. Let's go with purple. No, that's pretty rubbish as well. Blue. We know that that is a red cell from our previous red logic. Okay, so if these are all 8s, then where do we put an 8 in here? Can't go here by normal. That 8 here means it can't go there. I could have just made the... You know what? Let's do this better. Let's actually put the digit 8 in here. And, well, obviously not in there. I'm making a complete pig's ear of this. Let's put 8s in here, and we're hypothesizing that one of those two is an 8. Okay, now where do 8s go in this box? Well, it can't go there by normal, can't go there by normal, and it can't go there by normal, and it can't go there by knights, and it can't go there because it's not 9. 8 does not equal 9. So that breaks. Okay. Got there in the end, a little bit clumsily with some interesting, colourful additions. But the point is that, oh no, we've already said that can't be 8, and those can't be 8s either. And now that we've ruled an 8 out of that cell, that means that can't be a 9 anymore, because if that was a 9, then by the consecutive rule, that would have to be 8. So that's not a 9, and in fact that tells us where our remaining 9s are by normal Sudoku. Okay. In fact, do we know? No, we don't know. Okay. I was just checking if there was something that I'd overlooked in the logic, but no, it's to no avail. Right, let's just do a little bit more marking on 8s. In this box, it can't go in here because of these two 8s, and it can't go in here, and it can't go in here. So it's one of those two. But yeah, beyond that point, there's not really much more we can do with 8s, I don't think, unless there's something, like I say, that I have missed. Alright, so you might be looking at this board in its current state and wondering what on earth you do next. I think there is some progress you can make by just going through combinations in the middle box, because obviously we do have quite a lot of information about the middle box. But there is a very clever trick, one that is that I find extremely satisfying to look out for next. Spotted it yet? Maybe. Maybe you have. It's these two cells here. Now, what do we know about these two cells? Well, let's just mark in every possible candidate. Okay, obviously neither of them are 9 because we've already got all of the 9s in the grid. And that 8 sees that by normal and that by knights. So those cannot be 8s. So they're just 1, 2, 3, 4, 5, 6 or 7, right? Wrong. Now, do you remember these 5 cells, because of our red region logic, must be all 5 of the digits 1, 2, 3, 5 and 6. Now if you look carefully, all 5 of them see both of those cells. So that cell sees that by nights, normal, normal, and nights. And that sees that by normal, nights, 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 and nights. So these cells cannot be any of the digits that are going into those 5 cells. They cannot be 1, 2, 3, 5, or 6, and all of a sudden we're down to 2 candidates. And we know they must be different anyway because of our diagonal constraint. So everything is working together to tell us that this is a 4-7 pair. One of them is 4, one of them is 7. We can do a similar thing up here. It's not quite as powerful up here, but we can say that, well, let's put everything in. Why not? Well, they're not 9s, and they also can't be 1, 3, or 4 because they both see all 3 of those cells. So they can't be 1, 3, 4, and also because of this 4-7 pair down here, they also can't be 7. Now this one here can't be an 8. And there's another bit of logic we could have done here that's not too difficult actually, and it's to do with this Kropke dot. What can we put on the Kropke dot? Well, we can't put 1, 3, 4, 8, or 9. Can we put 2 on there? Well, no, because it would have to be paired with a 1 or a 3, and the 1 and 3 are both taken. So it must be 2 digits out of 5, 6, and 7. And one of them must be 6, because obviously it can't be 5 and 7. They are not consecutive, so one of those is 6, so that can't be a 6. Right, now let's have a look at the interaction between this cell and these cells. We know that this is either 2 and 7 or 4 and 5. If it's 2 and 7, then wherever the 2 goes, it either sees that cell by normal Sudoku or by Knight's move. So that can't be a 2 anymore, so it ends up being a 5. So if there's a 2 in here, there's a 5 there. And all 3 of those cells see that. That by Knights, and that by the diagonal constraint. So if there's a 2 there, that puts a 5 there, and that can't be 2 or 5. Similarly, if there's a 5 there, if it's a 4-5 pair, that can't be 5, so it must be 2. And then we have a 5 and a 2 seeing that cell again. So either way, this cannot be 2 or 5. Right, it is at this point where we do just have to think about combinations and eliminating possibilities from this arrow. So we're going to do my favourite thing and put in every possible candidate. We can rule out 9 because we've got all the 9s, it's just not 9. And we can rule out 1 and 2 because we can never put 1 or 2 in the circle of an arrow where there are 2 digits that are different, adding up to it. That was a very long-winded way of saying it, but yes, I'm sure you know what I mean. Now, if this is a 3, then this becomes a 1-2 pair, and then what can that be? If that's a 1, that would have to be a 2, but we've already got a 2 there, and if that's a 2, then that would have to be a 1 or 3, but we've already got a 1 and a 3 here. Just not going to work. So that cannot be 3. If it's 4, then that 1 there, well, it must be a 1 and a 3, and that 1 there tells us that would have to be there, and then that would be the 3, and that would be a 2 to be consecutive with the 1, that would be a 5, that would end up being 6 and 7. Yeah, there's nothing really contradicting this yet, so we'll come back to this. Feel free to treat that as a spoiler alert or not. So it could be 4. Let's try out 5. If it's 5, well, that immediately makes that 2, which means this can't be a 3 and a 2, so it must be a 1 and a 4. And because of that 1 there, the 1 must go there, and then this can't be 2 anymore because we've already got a 2 in the box. So that breaks, so it can't be 5. It can't be 6 because there's a 6 in the column already, either there or there. Can it be 7? Well, if it's 7, that makes that a 4, which means this can't be 4, 3. It also can't be 2 and 5 because there's a 2, 5 pair just here. So it must be 1 and 6. Then the 1 ends up going there because of that. That becomes the 6. That becomes a 2 to be consecutive with the 1. And that 2 makes that a 5. And that breaks this, because we know that we need one of 5 and 7 to go in here, and so that denies both of them as possibilities. So that doesn't work, so we can go back and say that that is not a 7. So we've narrowed it down to 2 possibilities. Can it be 8? Well, we've got 3 possibilities for 8. Can it be 1 and 7? Well, let's put a 7 there and a 1 there. Obviously the 1 pushes it down there, so that makes that a 2. That makes that a 5. That makes this a 4, because it can't be 7 anymore. And then we've got a 3 and a 6 to place, but the 6 can't go here because of the 6 in here, and it can't go there because it's not consecutive with 4. So that does not work. So this cannot be a 1 and a 7. Can it be a 2 and a 6? Well, if it's a 2 and a 6, then that makes that a 5, which makes this 6 and 7. What do we know? What do we know? Oh yes, right. So this cell, if this is a 6, then that has to be a 5 or a 7. It can't be a 5 anymore, so it must be a 7, but that cell sees both of these by normal Sudoku there and by knight's move there, so that can't be a 7 anyway. So it can't be a 7 or a 5, so this can't be a 6, it must be a 2, which makes that a 6. But that breaks because now we've got a 6 and an 8 pointing at this cell here. So that cell could no longer be an 8 or a 6 if this is a 6-2 pair. So that doesn't work. So we can't make it 2 and 6. Can we make it 3 and 5? This is the only possibility left if this is going to be an 8. Can this be 3 and 5? Well, the 5 in there would make that a 2. We've already said that this can't be a 7 because it sees both of a 4-7 pair by normal and by knights, and obviously for the same reason that can't be a 4 either, so that can't be a 2 or a 4, which means it can't be consecutive with 3. So it would have to be 5, and we've already said it can't be a 4, so it would have to be a 6 there and a 3 there. Now I think there is a way to disprove this that is boring, but the exciting way, the way that I absolutely love, I think is absolutely hilarious, is that this cell, if it's adjacent to, if it's consecutive with 4 or 7, then it must be a 3, 5, 6 or 8. And we end up with a 3, 5, 6, 8 quadruple seeing a 3, 5, 6, 8 quadruple, and it just doesn't work. We'll kind of end up with a 3, 5, 6, 8 quintuple, if you like. I mean, there are different ways of thinking about it, but I just quite like that these 4 cells rule out every single possibility of, even though there are 4 possibilities here, all 4 of them end up being ruled out by this combination. Maybe it's not as interesting as I'm making it seem, but anyway. The point is, this can't be 3 and 5, and so we've gone through every possibility to make this 8, so it can't be an 8 anymore, so it must be a 4. To be honest, from this point onwards in the Sudoku, it does begin to fall apart a little bit. It becomes a lot easier. So again, there's a slightly, arguably unsatisfying bit of logic here, just kind of going through all the combinations and seeing what's possible. It's probably possible to do it in a much more elegant and quick way than that, but I quite like some of the kind of disproofs of each combination that could potentially have been possible. But anyway, we do end up with a 4 there. That means that these two have to be 3 and 1, and that 1 tells us that it's this way round. Now, to be consecutive with 1, this must be 2. That makes this 5. So this can't be 5 anymore. It must be a 6-7 pair. This 4 tells us that the 7 is there, and the 6 in there tells us that has to be a 6. And now that is an 8. So we've completed our middle box out of nowhere. Well, not out of nowhere, really. This one now sees that by knight's move and that by normal, so that must be a 1, and it also sees that by knight's move and that by normal, so that must be a 1. So those are the 1s done in the red region. this 3 also knocks a 3 into here, and a 4 into there. This isn't a 2 or 3 anymore because of those, and the 5 and the 6 in here rule that out. We could have actually said that's not a 6 a long time ago, because it sees all 3 of these squares, that by normal and those 2 by knight's move, and we know that there must be a 6 in one of those 3 squares, so that's a potentially neat way of ruling that out. Okay, this can't be 4 and 5 anymore, because this 5 sees that by normal and that by knights, so the 5 has nowhere to go in here, so it must be a 2-7 pair. And now, because of what we know from our red region logic, this is not 2-7 anymore, it must be 4-5, and that 4 resolves it. We can also spot, I mean, there's plenty of things that we can spot at this point, so you're probably screaming at the screen saying, why haven't you spotted this yet? But yeah, I'm working through it slowly but surely. I'm just going through one possible path. I mean, like I said, once you've got that 4, it does all begin to fall apart. There is a 7 in one of those 2 cells, and they both see that cell, so that now must be a 6. We can't have a 6 in there anymore. Now, what else do we know? This can't be a 5, which means that can't be a 3, because if that was a 3, then that would have to be a 5 to make up the 8. This can't be a 2, and that can't be a 6 by normal Sudoku as well. And I think, I certainly hope, that at this point you get stuck. Oh no, there's some more that you can do. Because we know that's not a 7 anymore, so it must be a 4. Yeah, I think this is the point where you need to spot this column, which it's not groundbreaking logic. No, alright, no, I won't rave about this, I'll just get on with it. This is a 2 or a 3, it's the only thing left in the column, and it can't be 2 because of knight's move. Okay, so a 3 there and a 2 there. That now means that in order to complete this arrow, that needs to be a 6. And now, because of our red region logic, that can't be 2 and 6 anymore, because we've already got 1, 2 and 6 in our red region, so it must be 3 and 5, and it must be that way round. Okay, where do we look next? This is 2, 5 and 8, except that 5 sees those 2 by normal and by knights, so that's the 5. And we already said that can't, oh yeah, because of knight's move, so that's not an 8, that's a 2, that's an 8. And what else do we know? This is 2, 4, 6 and 7. Do we know anything about that? No, maybe not yet. There's a 2 and a 7 there, so that must be 4 and 6, and we know it's that way round. And then actually the 2 there sees that by knight's move, so that's 2, that's 7, and that resolves this 2, 7 over here. Really beginning to fall apart. So in fact, can we finish this diagonal? Is that worth thinking about? It's we've already got 1, 4, 5, 7 and 9, so we need 2, 3, 6 and 8. That's not a 2. Whoops, that's not a 2. That's not an 8. If that was a 6, that would rule out 6s from both of those, so that's not a 6. In fact, that's not a 6 either. Alright, what else can we do? Oh, this needs a 3 and a 1 in this row. I'm kind of jumping about all over the place here, but at this point, we just need to get it done. What do we need in this box? We need 1, 2, 3, 4, 5. The 3 is a bit restricted. It can't go there, and it can't go there by knight's move, so it must be there or there. And now that we've got that, that can't be a 3 anymore, because it sees that by normal and that by knights. So putting a 3 there would rule out all of the possibilities in that box. So that must be a 1. That must be a 3. And that rules out a 3 from there, so that's an 8. That makes that a 6. That makes that a 7 and a 6. What else do we know? There's a 7 there or there. We've not got that yet. No, maybe not. We've got 6 and 8 now, so that's not 6 or 8. Still not quite resolving it. what's left in here? We need 4, 5, 7 and 8, except these aren't 4 and 5, and these aren't 7 and 8, and that 4 resolves it. Well, plenty of stuff resolves it for us. That's 5 and that's 4, and that 7 and 8 isn't quite resolved yet. Okay, let's keep pressing on then. What about this column? 1, 2, 3 and 5. Well, the only place for a 5 in the column is there. That's seen because of that, and that is seen. So that's a 5. That's not a 1. That gives us a 2, 3 pair in case that's interesting. That's not a 2. That's not a 3. Anything else? Oh, that's not a 1 by knight's move, so that is a 2. That makes that a 3. That makes that a 2. That makes that a 1. That's a 3. We're getting there slowly but surely. Now in this box, the only space left for a 3 is here. That, if we trust our pencil marks, that means that is an 8. This is 6 and 7 in some order. That means that a 7 in this box has to go here, and that resolves our 7-8 pair down here, which resolves this 7-8 pair. There's a 7 up here. We got that yet? Oh, we need an 8 in here. We can write that in. I think that's all the 8s. Oh, apart from there. Where are our remaining 7s? Oh, yes, that's seen by knight's move, so that ends up being a 7 along with that one. So that becomes a 6. And now we need our last 6 over here. Have we got? Oh, we've got one more to place, and it's there. That's 4 and 5 that way round. That's a 1. Can we complete this box? 2, 4 and 5. Yeah, it's pretty much done now. We need 1, 2, 3, 4 and 5 in here. That's 4, 2, 3, 1, 5, and that's a 1. And that is the Sudoku complete. Yeah, so that last kind of third or so of the solution is pretty straightforward. Once you've got that 4, yeah, it all just kind of crumbles from there, and it becomes, you get rewarded for the hard work that you did in the first 2/3 or so of the Sudoku. Yeah, it's a tricky break-in, and there are times when it's not obvious what to ask, but if you get the right questions, you get the right answers, and you get the right solution. Yes, for the second week running, I've had to post-edit a rambly outro. It's because I still haven't worked out a way of asking you to like, comment and subscribe without it just sounding like some kind of awkward parody of every other YouTuber on the planet. But it genuinely is very much appreciated if you can spare a second to do those things. But otherwise, thank you very much for watching, and enjoy the rest of your week.